There is a growing weak spot in Earth's magnetic shield, stretching over the South Atlantic Ocean and parts of South America. It is known as the South Atlantic Anomaly, or SAA. This strange region is not just a scientific curiosity. It is a hazard that space agencies monitor daily. Satellites crossing this zone experience higher radiation levels, electronics can glitch, and even the Hubble Space Telescope suspends observations when passing through. NASA has called it a dent in Earth's magnetic field, and new research shows this dent is not stable. It is expanding, drifting, and even splitting into multiple lobes. The anomaly exists because Earth's magnetic field is not uniform. The planet's magnetic shield is generated by the geodynamo, the flow of molten iron in Earth's outer core, roughly 3,000 kilometers beneath our feet. These turbulent flows generate electric currents, which in turn produce the protective magnetic field that deflects much of the solar and cosmic radiation constantly bombarding Earth. But this dynamo is not fixed. It shifts and fluctuates. Over the past 180 years, scientists have measured a roughly 9% decline in the strength of Earth's dipole field. That weakening does not necessarily mean catastrophe, but it does create opportunities for anomalies like the SAA to grow stronger and more disruptive. In the South Atlantic, one theory links the anomaly to a colossal structure deep inside the planet, the African Large Low Shear Velocity Province. This vast region of dense rock at the boundary between the mantle and core appears to disrupt the flow of molten metal. The result is a distorted magnetic field at the surface, creating patches of weakened or reversed flux. The South Atlantic Anomaly is one such patch, essentially a pothole in Earth's magnetic defenses. Geological and paleomagnetic records even suggest that disturbances in this region may have persisted for millions of years, though their size and shape evolve with time. Today, satellite data reveals that the SAA is not stationary. Its center drifts westward by about 1/3 of a degree each year, which translates to tens of kilometers of movement annually. And since around 2020, researchers have detected that the anomaly's minimum has split into two distinct lobes, one closer to South America and another toward Africa. This evolution hints at deeper changes in the core's flow patterns, reinforcing the idea that Earth's magnetic field is in constant flux. For satellites, this region is one of the most dangerous areas in orbit. The Hubble Space Telescope deliberately avoids taking scientific observations while passing through the SAA, because detectors are bombarded with high-energy particles that could damage instruments or corrupt data. Satellites in low Earth orbit, from weather monitors to CubeSats, experience elevated rates of single-event upsets, where a single charged particle flips a bit in memory or triggers a fault in electronics. To counter this, engineers design spacecraft with radiation-hardened components, error-correcting memory systems, and autonomous safe modes that protect the mission when anomalies occur. Despite these defenses, the SAA remains one of the primary challenges of operating in orbit. It is important to stress that this anomaly does not pose a direct danger to people on the ground. Earth's thick atmosphere absorbs most of the extra radiation. The real risk is to satellites and space missions, and by extension, to the global systems that depend on them: navigation, communication, weather monitoring, and even elements of the power grid. The growth of the South Atlantic Anomaly naturally raises another question. Is this the beginning of a magnetic pole reversal? Earth's poles have flipped many times throughout geologic history, on average every few 100,000 years. During these reversals, the field weakens, becomes chaotic, and then rebuilds with opposite polarity. Some scientists speculate that the present-day dipole weakening and the growth of anomalies like the SAA could be precursors to such an event. But NASA and ESA emphasize that there is no evidence of an imminent reversal. What we are witnessing is more likely secular variation, the normal, though sometimes dramatic, shifting of the magnetic field over decades and centuries. Still, the consequences of a weakened field are real. A weaker shield means Earth becomes more vulnerable to solar storms, bursts of radiation from the sun that can already disrupt satellites and, in extreme cases, damage terrestrial power grids. The SAA, by exposing spacecraft to heightened radiation, provides a glimpse of what a generally weaker global field might mean for technology and exploration. Scientists are racing to better understand and predict the anomaly. ESA's swarm constellation of satellites continuously measures the magnetic field, while NASA and other agencies update models of the anomaly's drift and structure. Engineers incorporate these models into spacecraft operations, adjusting mission plans to account for the SAA's shifting boundaries. What they are watching most closely is whether the two-lobe structure continues to evolve, whether the westward drift speeds up or slows down, and whether the deep Earth link to the African LLSVP can be confirmed. Each of these questions holds clues about the dynamics of Earth's core and the future of our magnetic shield. The South Atlantic Anomaly is not a sign of impending disaster, but it is a vivid reminder that Earth is a living planet. The magnetic field that protects us is dynamic, unpredictable, and shaped by forces deep below the surface. For now, we can adapt. Satellites can be hardened, missions can be planned around the anomaly, and scientists can refine their models. But the SAA also teaches us humility. Our planet's hidden engine is powerful, restless, and only partly understood. As this anomaly continues to expand and evolve, one question lingers. Are we simply watching a natural fluctuation, or are we witnessing the early hints of a much larger transformation in Earth's magnetic future?